Okay, I think we have Dr. Uday Kala with us right now.
Yes, I'm very well.
Yeah, thank you for confirming. I think we will start again on time. So, in the meanwhile, you share your screen, sir. I would just like to welcome again everyone. So now we already have our next speaker with us, Dr. Venkat Udekala, who will be presenting on nature-based reinforcement research towards application. Dr. KV Uday, Chairperson of the Center of Climate Change and Disaster Management at IIT Mandi, specialized in landslide risk reduction, smart geotechniques, and nature-based solutions. He has more than 15 years of experience and has 6 plus CR INR research and consultancy funds, 70 plus publications, 8 patents, one startup experience, and has led more than 6 crores INR research and consultancy funds. On this note, I would like to invite Dr. Uday Kala.
Okay, thank you very much for first of all for making me giving me an opportunity to be presenting the work which I'm trying to do, and it would be really wonderful to have some suggestions coming out to the end of the presentation. I was looking at the enthusiastic participants, and I'm very happy to see definitely some outcome coming from the presentation through questions, and I'll be more than happy to take it to the end of the presentation or the time which has been given already. So for the next time or next 30 minutes typically, which is allotted to me for the presentation, I will be bringing down a concept which we have started to understand, develop, and as we are moving forward in this particular domain of nature-based reinforcement. Given that we want to understand from the nature and also try to tune so that we are making it more towards engineering, then adopting it as a same part. But before this, I just wanted to again re-incite the presentation, which was yesterday exactly at the same time at 2 o'clock, who have already given us a very good idea on the soil and plant interaction. And based on this, how they took it to the field and accordingly nurtured it to the requirement which solves the problem immediately. Probably to the end of this particular presentation, I will be giving you again a similar line. However, the approach and the other identity we are trying to bring in as a part of this particular work, which is done at IIT Mandi, expectedly should give you a different perspective. That's the main focus of this presentation. As we move further, I have a habit of presenting first IIT Mandi, being in the Serene Valley of Himalayan region. We are in the mid-Himalayan zone, roughly around 1,000 feet, 1,000 meters above the mean sea level. We have different campuses given we have we have to settle in valleys, typically like a very hilly establishment. So you can see a campus over here, a campus over here, and there is a connection of road. And we have Snow Peak Mountains just behind the campus, as you can see, and also we have a lively river which is running across the stream. While we have these benefits, undoubtedly, when you are in this particular domain, I'm sure in the last 2 weeks, you would have seen a lot of these particular things in your WhatsApp videos, forwards, news, and other articles. That a disaster is a very regular condition for Himalayan region, especially because of the changing climate, changing terrain, changing conditions, plus the need to construct roads, plus the need to people to develop infrastructure and all this facility on this. These photos which I'm trying to show you are typically the landslides which you encounter while you are traveling from the district headquarters of Mandi towards IIT Mandi campus, roughly around 19 kilometers, 40 minutes of travel, and you're going to see 80 plus landslides in this particular location. A few things which I have clearly mentioned in this particular photo, if you can see, is we have different types of terrain. We have rocky soil, we have debris soil, we have a very shallow landslide, as probably you are seeing here, and also here, very shallow, but extended to vast. The next important thing, again, you should catch up in your mind, because the title I have already talked about nature, and I also told you the presentation yesterday yesterday at the same time regarding the plant and soil. So as you can clearly see, all of this what you're seeing are vegetative slopes. Then the question comes, we claim a lot on bioengineering, slope protection, and all these particular aspects, but then why are we missing, or what is missing in this particular aspect to not make it to look into the bioengineering aspects? That when you see this particular slide, so much of green car, but still I have a very good shallow failure, which probably you can see in this particular location. Shallow I am mentioning again because the moment I will start talking about bioengineering, root soil interaction, deep surfaces are difficult to be dealt, but shallow, like probably what you're seeing on this particular site, should not be expected, or I am not expecting definitely as a researcher, that when the thickness of the slide is not very much, why should it still be happening when there is already a dense vegetation in this particular location? So to dwell into this, we started looking into the literature. We started to understand, and it's a very well applied situation that vegetation is definitely one of the major reinforcement processes in the soil, which will help the soil to be binded, located in place, and also control the soil moisture movements inside and outside the soil. Then there are again various methods which have been brought in on the name of bioengineering to bring in how the slopes can be constructed by using various methods of bringing in nature-based solutions, as we are talking again about different types of. Again, these three images, if you can see, well published in literature, they talk about the plant, they talk about the root, they talk about the branch, they talk about the leaves, and the association, how each of them are bringing into this. However, being again on the campus of IIT Mandi, looking so much of failures, the question always comes back is what is missing again in the whole of this particular setup. That was the major objective, but by which we looked into the literature, which clearly shows that there is something what a plant requires from the soil, and because it is nature, then the plant gives back something to the soil. In between both of this, when we are talking, we talk about life the plant is getting from the soil, and the strength which is coming back from the soil to the tree. Well, this again is established, and a lot of people started to look at. There are a lot of root reinforcement models which was started somewhere as good as in 1970s, 1960s. People started to talk very much in the mechanics and scientific domain of how the roots are going to be interacting with the soil. Different models, different methods, different softwares, different options you have these days to look into the engineering. However, the concept which we understood is how the part of nature-based solution is missing the part of engineering. So we simply took out the same concepts of nailing and uh, reinforcement, and we tried to see how that can be applied to different of these particular species of plants, and come to a concept of engineering to conform bioengineering. So we identified a very indigenous plant species of Mandi domain. I did not want to bring in the species or the plants which are from outside this particular area. I did not want to bring in the unnecessary aspects of invasion of different species. However, few of these of them are already invaded almost like 500, 600 years ago. That is very clear. Again, wary of those who probably know on this particular domain, I'm sure you are looking of these 18 plants. You are looking for one particular species called as vetiver, which is missing in the list, or should I say, which did not make to the list of two constraints. Number one, by which the vetiver is not a very regular plant or indigenous plant of this particular region of Himachal Pradesh. Number one. Number two, thanks to NIDM, Professor Chandan Ghosh, he has given me almost like 15 different type of different species of vetivers, which we have planted in our bioengineering our botanical garden. Unfortunately, none of the vetiver has given me anything better than half meter of root. So the soil clearly is mentioning that, don't bring in vetiver here. I'm not ready to take it as a regular plant in this particular domain. So we continue with these particular 8 plants. We get in species, we get in the plants we have planted in our trees, and we try to identify which type of species of this are more abundant, what type of structure it is. And fortunately, if you look into, we are not simply selecting trees. We are also talking about a combination of the vegetation coming in as grass, as shrubs and herbs in the whole of this particular expectation. So we brought in the comparison between a soil nail and a plant root. When you look at, probably soil nail is very, very simple, very easy given the conditions that it has a fixed diameter. You have an option of choosing the diameter, you have an option of choosing the strength, you have an option of understanding the type of material, what is the type of system, FE, the different types of reinforcement methods which have come in, which are alloy based. You already mentioned it saying, 400 species, 300 species, 200, sorry, not species, 200 material, 300 material, talking about the tensile strength and the grip tensile strength. Then you can also interface the angles and, holding capacity, pull out capacity, and all these things. Unfortunately, these particular options of choosing is probably missing in this plant roots. That the diameters are varying, not only varying in the structure, but also varying with respect to time, varying with respect to the location of the plant itself. Availability of water, availability of geotechnical or sorry, geological conditions of this particular soil, and added to the environmental aspects, the roots change with respect to time, with respect to conditions as well. Then they are also having variable strength. It's not that the whole of the root is giving you only one particular strength. The roots change their strength, and then this thing. Orientation and shape probably gives you the best of the conditions here, because it enters only into the void spaces and holds or grips the soil definitely better than a regular drilled or a grouted nail condition. Finally, we talk about the big point, which we call it as sustainability, that the plant gives you not only a natural green as well as this. Again, acknowledging the discussion yesterday, that unfortunately you need time for the plant to grow in a given condition and take out all the mechanical aspects as we are discussing here. While steel nail or the nail, which is an engineered material, is adapted to the site depending on the feasibility and it can be erected in a very short time. That was again a discussion which is brought in. However, I bring into the condition that probably when we talk about the bioengineering, we are not talking about a remedial measure. Sorry, it is considered to be a remedial measure, not as a reinforcement material or not exactly as a embedded material. So it is more like a Ayurveda, that you need to spend that amount of time for your body to grow naturally, for your body to adapt to the situation and give the inner strength. That is exactly the concept what we try to look into when we talk about the different roots and their structure to the soil and thereby the reinforcement. We selected different plants as just we discussed in the last slide, different diameters, different root, different webbing culture, or the 3D structure if you look into this. And if you ask me, okay, what is the root diameter? Then I have a number of diameters. It's not well, some of the plants or the species like this have a taproot, less taproot, higher taproot, more fibers or more fibrous root, no presence of at all any taproot. So you can see these are all natural, and it's expected that most of these plants which have a taproot or a fiber root are going to continue with the same condition, unless some geological formation is going to change the looking of the plant itself. So now the question comes, how to characterize or how to quantify these particular systems. Then by using the simple existing system, we understood that we are going to add a component of apparent cohesion into the system to see how the strength is increasing in the plants. The research is ongoing, as we discussed, starting from somewhere around 1970, 1960 itself. So it has been already discussed quite well in the literature, saying that RAR is a factor. What we call it as root area ratio is a major factor, which is going to talk about the architectural parameter. Whereas the strength of the plant or the strength of the root itself is a major component, which will also add the strength to this particular component of shear strength. All these components again well established into this particular domain. If you just look into quick literature, I'm sure you're going to get a lot of idea on this particular aspect, where we talk about now when we bring this root in the soil in the lab, we try to desegment the different types of root, different diameters, different lengths, different grip lengths. Then we use micro UTMs. We try to get the stress strain behavior of this particular material. And if you can probably appreciate this part, the error bar in all this particular set for a given diameter, for a given conditions, for a given strain rate is too high, because as we are discussing again and again, it's a natural material and it has its own mode of failure and times of failure. So we started to establish this particular aspect. Finally, when I look into different types of these systems or the plant species, almost equivalent in number, when I'm trying to find them, they are definitely forming as a cloud, while only few of the plants are giving me very high strength or high strength in this particular aspect. Whereas their maximum of the species are giving me a controlled cloud, what I call it as a very normal or a mediocre strength. So we thought to understand how to develop this particular aspect. The second aspect, strength, is okay. We understood the strength part of it, the variations and opportunities. The moment you come into this RAR called as root area ratio, it's difficult to get into a concept of diameter. So RAR has been introduced. Again, when we say RAR, we have not a very specific method by which you can determine the RAR. While the formulas are very clearly given, it becomes very difficult thanks to image processing and improved image processing over the time, that we are now able to segment the image in a plant or in that particular root to understand how this root area is changing with respect to the structure. Probably in the next slide, you will be getting an idea why this is very important. So we also tapped in that root area ratio, that how much of the root can be covering a particular area or covering a particular domain when it is present inside the soil. So now going back to the DBITS 2008 option, we can quickly find out what is the improvement in the cohesion because of the presence of the plant root corresponding to what already the soil has as inherent property or the property of the soil itself. So this is an extra component which is added to the cohesion component of the soil. So now when we look into the RAR profiles, a simple philosophical idea comes in, that this RAR can tap a different opportunity or different application potential itself. While I will say something which is not going much in the depth, but giving me a slightly good strength as it is increasing over the depth, I say this is more of a surface erosion or a superficial application species. Whereas if it is increasing over the depth, then I am seeing it to have a good opportunity of being a reinforcement material, the way we are talking about soil nails or any of these conditions. However, when you're talking about all this, don't forget that we cannot go to the depth what a nail goes. So feasibility is definitely a major aspect which you have to look in before talking about this. So again, you can see some plants which are trying to give me slightly higher strength on the top, but the moment it is going down, it is going to tap a different conditions of all this. So we have to understand that it's not a particular species is going to solve me a given problem. So we have coined in the concept of community of plants as we are moving forward. So for this, we wanted to understand or rate or rank a particular plant, how to choose that particular plant or a particular species in order to make it more workable in this particular option. So we try to rank the species based on the two components, RAR and tensile strength. Undoubtedly, both of them combined, we are getting a root cohesion itself. So we can understand how much of that particular root and soil are contributing to the extra component of cohesion as root cohesion. Based on this ranking, now we are coming to a concept that, okay, if this is the arrangement of the plant, if it can be planned, that higher tensile strength of the material goes in between, or a combination which looks as the way we are trying to depict here. However, the higher tensile strength plants are more present on the top and the bottom line, and slightly lower tensile strength but higher RAR are present in this particular domain, where tensile strength is less, but tensile strength is more, but also the RAR, the root spread, is also confined or controlled. So we are talking about a high grade system which can be developed. It's not, again, we are not simply saying that go and plant one species of plant across the whole slope. We are talking about now the condition of, can you split the species so that we are maximizing the effort from this particular option. So we are trying to see how we are trying to perform now more of numerical models by which this particular aspect can be strengthened by using the concept, go to experiments and try to find out. So in the meantime, we understood few of the plants are giving me a high erosion prevention option. So we try to catch the low hanging fruit. So we brought in a simple erosion setup. We try to set up a erosion flume, which is trying to give us an option of segregating. Again, I have used image processing in this to find the time rate of erosion which is happening on the site. So by this, we can simply quantify that there are few conditions, or few conditions in this particular soil which are inducing splash induced. The moment there is a raindrop falling on the soil loses from its place and going on. However, few of them, while they are not showing me any splash induced, they are showing me runoff induced, which means over the time when the rainfall is continuous, then you will see more of erosion happening after a particular time. So we try to split these two and try to see which of this particular material, especially we talked about the different grass species, as we are talking about a very thin or a superficial condition on this. So we try to quantify how the bioengineering can be controlled in this particular condition, where initially when the soil gave me something around 4 kg of sediment at a given time and a given rainfall conditions, the moment we started to use a simple fiber, we started to see a reduction in the in this material. While going to the grass, we had again two options. One is not to use leaves. So when I'm talking about this grass conditions, I did not use the leaves. I simply used the only grass. So I have planted the soil on the in my flume, and I have removed the leaves from the top. So why am I doing this? Because probably it will come in the next stage. However, the simple cutoff is I want to still see that splash induced rainfall coming into the picture where there is no leaf. So the raindrop still has the same potential by the time it is touching the layer of the soil. So my grass is now acting as a reinforcement material. Only reinforcement. I'm not stopping any energy in going into the soil. So there I can see a quick reduction in the sediment. What am I collecting in this particular domain? The moment I add the leaves for the given grass, say for example, in this I see that Indian goose grass is giving me the least by the roots itself. So I simply allowed now the leaves to be present in the on the soil, so that I want to see how much of these leaves are coming into picture, and the results are definitely spontaneous, which it shows that the splash induced or most of the erosion now we understood from this coming is the splash induced erosion itself. So we reduce the splash by using leaves, whereas runoff induced sediment is also reduced because of the presence of the grass itself. So we have come up with this particular concept where you can very clearly see the changes in the across this particular thing. However, I hope it's no point showing you an image with a plant and or a leaf, because you cannot see any soil below, and the sediment itself is clearly saying that erosion can be very well controlled by using the grass leaves. Sorry, by a simple grass, which again is a very common grass across India. I understand why that is why it is called as Indian goose grass, which is a very good option. Again, these results are confined with the amount of with the soil and the plants which you have selected for this particular. Finally, if I have to conclude what we have developed from this is the whole system of the plant works very well for the for reducing the effects or the contributes to the improvement in the soil strength, starting from the leaves, as just now I told you that it leaf is the component which is looking at the soil and water balance. Further, avoiding the intensity of raindrops or absorbing the energy from the raindrops, not to reach the soil directly. The remaining stem is the one which is going to give me, again at the surface level, it is going to give me a rate of reduction where the soil or the sediment transport will no more happen because of the intersection of the stem at the interface or at that particular point. And finally, the roots acting as a reinforcement system into the ground and trying to avoid the moisture coming in. And before this, we also talked about the importance of different species getting into the picture to reduce the effect or the efforts of the species of the sorry to improve the strength of the soil and thereby increase the surface or subsurface subsurface or shallow landslide conditions coming in these particular domains. So this is what we have understood with the plants. Now, quickly, with the paucity of time, I'll quickly move to the other topic, which I call it as biocementation. I'm sure these days the biological or the nature-based solutions also include a lot of bio-based materials, thanks to the improving biotechnology, which is really creating a conditions where we can bring in the species of bacteria or the enzymes from the soils or the plants. Sorry, from the bacteria or the plants in order to make it more workable for us. So in this, we also started to look into this particular domain called as biocementation, where we talk about the process called urea hydrolysis or denitrification. We can use it for sulfate reduction. We can use it for iron reduction. So we can treat the soil or treat the problem of the soil within the soil itself by using this concept. Now, people have been using these concepts for decontaminating the soils and improving the conditions of the soil. I'm sure you should have been seeing a lot of videos coming on from like China is treating deserts and increasing the plant cover in the deserts, etc. So now we understand if you can treat the soil with the particular species of bacteria, look into how you can improve the nitrogen content in the soil and give a life into the soil. I'm sure you should be able to now develop uh, like these conditions. I'm sure they can be easily solved. This is what we have tried to understand. However, I wanted to look into how these particular aspects of soil can improve the strength itself in the soil. That's what probably most of the geotechnical engineers look at to improve the strength and stability aspects in the soil. So thereby we try to understand how this bacteria cell is going to create a condition in the soil by which we can increase the calcite precipitation, the way we call it as cement addition to the soil or lime addition to the soil, which have now become unsustainable, or now we have started talking about zero net emission policies and all this coming into the picture. Now I'm sure this particular topic will in India, at least across the world, will now be improving to the conditions where we'll now talking about natural conditions by which we are releasing the calcites or the or in different words cement directly into the soil without coming into any of your process of hydrolysis, sorry, process of hydrolysis or the strength gain in the soil for the conditions. So we simply took out different types of soil, a soil which is probably again a poorly graded soil, thanks to the first presenter today, where we understood the decreasing in the good quality available sand in the world. So we have to definitely now talk about the material which is not no more coming into that as zone 1, zone 2, zone 3 set of conditions. And I wanted to bring in how this particular sand can improve given the conditions of reinforcement in the soil. I have taken up a simple geotextile, the non-moving geotextile, as you can clearly see in this particular image. And the regular experiment, what we try to do about the sand and the geotechnical and the geotextile interface in the soils. I wanted to see how MICP or this EICP or these bacterial processes can come in and improve the conditions. So we have taken the soil, we added this bacteria, we try to move in the hydrolysis conditions or the conditions and try to see how the strength or the conditions are improved. As you can see, I'm targeting slightly lower densities, what you may not observe in a regular construction, only because the biomaterial needs space to breathe. So that particular process we need to definitely maintain on this. Only difference is in a regular condition, we use water to densify the soil, or while compaction we use the water. However, in these conditions, because I have to give a feed to the bacteria present in this, we use urease, which is again a very regular condition. To the amount of waste which we are generating on the ground, we can simply generate this urease in a very cheap quantities as well. So we took out the solutions. We tried to understand how the bacteria is going to give a condition where I'll be able to release the calcite directly into the soil. And I apply the soil, the grains, I applied the material into the soil, leave it for some time so that the calcification happens inside this particular ground. And we have different methods. First, I choose only to quantify or only to look into the cementation in this. The second, I try to only biocement. I'm trying to see only in the geotextile. And third, I'm making it as a whole system. I'm percolating the bacteria into the ground and trying to see. So I'm talking about three options while I'm talking about independently geotextile, independently soil, and as a combination itself, I'm trying to see how I can biocalcify the whole material. While I'm looking into this, we try to do this shear test to understand how the interfaces are improving over the time, before calcification, after calcification, during the calcification, and we try to develop a interface how it looks something like this. When I'm sharing, as you can very clearly see, when you understand a sand standing like this, try to understand that this bacteria which I have put into the sand have started to make this sand into a mortar, obviously improving the shear strength or improving the interface conditions of the material. Again, to start with, we talked about a poorly graded sand, which has been now converted into sandstone, possibly, and improving your interface. Obviously, the results will be interesting to see that the interface which was only developed between the sand and the interface was roughly around 30 degrees. Don't mind, I'm talking about the peak interface conditions. So that's why you'll see such a high values, while the values can be comparatively low as we are moving down. However, you can see I'm bringing the interface, or just if you try to see the increase which is happening from the 30 degrees 5 or interface to almost like 38 degrees 38 degrees, the interface is getting generated when we are talking about biocementation, which is improving the condition. Further, it might further when you look into this interface and the type of failures which you might be seeing, that the sand and the soil interfaces will clearly show you. So, for example, this is the place where I'm having lower amount of calcium. So, this two understand is an indication. If you are seeing 2, 4, 6, then 6 is the point at which I'm having the highest amount of structure. So these are the geotextile fibers which you see on an SEM. The moment you look into the biocemented sand now, the sand is now coagulated, or probably you will see a motor as a picture coming into this particular aspect. Whereas if you see the same thing happening here, when I'm looking at the system itself, probably the bacteria started to also enter into the fiber and started to reinforce or started to bind the fiber itself. So now I'm talking about a stiff geotextile and a stiff sand now interacting with each other. That is where you have seen the 30 degrees of interface coming into at this particular cycle. When I'm still talking about mediocre or four lesser or medium amount of cement which is generated, or sorry, medium amount of calcite which is generated here. The moment I'll talk about now 6 cycles, which means that I'm talking about now the highest amount of calcite present in this particular experimental process, then you can clearly see that now the geotextile is now giving me a tensile failure. I'm sure you'll appreciate the point that instead of the shear or interface failure at this, now it has pulled the geotextile to fail up to the extent of tension, which means I have probably maximized the condition of interface at this particular condition, which probably we'll try to look at when you really want to optimize the conditions. So the second option, what we quickly tried out is, can I simply look at, it might be difficult in the field to put bacteria, to put soil, to put conditions and all this. So we try to see how we can reduce this or make it down to the geotextile itself. We thought, can we play with the geotextile itself? So we added some bacteria to the geotextile, we treated the geotextile, and we could obtain a quick outcome where we have slightly made the geotextile stiffer and rough on the interface. To the best of the conditions, try to understand this is not cement, this is bacteria, or this is just a bacterial process or natural process in the field. So it is not going to give you any major effects because of this treatments or these processes. Leachate analysis and everything which has been done clearly shows that the life cycle assessment of this particular material is still standing to be a very good sustainable material itself, because every process we are talking is properly natural and purely degradable in nature. So as we move forward, so yes, here magic definitely happens, that at a very high displacement, still when we are talking about the interface angles have gone unbelievable to 45 degrees at the point at which I told you that now the geotextile itself is coming to the tensile pull because of the interface between the soil as well as the stiff soil and a stiffer geotextile coming into the picture. So we are now trying to bring it to a condition where now instead of geotextiles, can we bring in different materials, especially geogrids, to solve the same problem. Hopefully, when I get an opportunity next time, you should be able to see me publishing and as well as looking at this particular material. So based on these applications, we also looked at how different applications can be brought in by using the bacteria or the enzymatic solutions, which can help us to see which levels we can use, which type of material, etc. We are trying to bring in, and we also have patented this material, so that we wanted to see how it can be further improvised as we are going forward. So finally, if I have to conclude my talk, we talk about the nature-based solutions, both in terms of one, plant, second, bacteria, purely existing from nature, non-pathogenic in nature, and they only are we are trying to see how the nature material can help us to improve the conditions what we are trying to bring it in the soil. We discussed on the point, root area ratio is one of the major parameter to look into the adaptability when it comes to selection of a plant species, whereas tensile strength, because it has so much of redundancy, needs to get more confidence before we are looking at the applications and natural reinforcement as we are looking forward. Calcite precipitation is different from cement addition to the same soil because the calcite which we are adding is an extra addition, whereas when you add cement to the sand, you are adding extra to the soil. Or when you talk about 2% or 5% say cement, if you are adding to the soil, we are talking about replacement of the material with cement. However, when I talk about this particular option, I'm adding bacteria and enzyme and I'm taking calcites. So try to understand the difference. And secondly, this calcite, whatever I'm going to get, is going to be deposited only in the voids, not exactly not exactly on the grains. So it is not again the same what cement gives you. It is a totally natural material, and it is going to give you the best combination of bonding and bridging in the soil particles. Thereby, the interface of the geotextile is improving. It is not simply that it is cementing, or it is like the way you see in the sand. You are holding it, and you are holding it rough or tight. This is again a very condition. And when you use bacterial conditions, because they have to survive themselves, what we call it as a facultative bacteria, because they have to sustain themselves, they are not going to clog 100% of your soil, uh, not allowing water or any seepage or anything to happen. The seepage can still be happening. However, it is controlled compared to the earlier conditions. But again, like the way you use cement, it is not that you're going to 100% block the voids, or this particular concept. Corresponding to the same percentage calcites or calcium content we are talking about either in the cases. So we need to look at how you can easily use this particular material. Only thing which adds here is the time. You may need to give the time for the bacteria also to work and generate that calcites. However, bacteria can work deep into the ground, so you not wait for the bacteria to work exactly. You need to wait for the bacteria to give you the final result. So the work can still continue without any hamperage. However, the confirmation of those particular results we need to check out after having a lot of field-based tests and everything, which is still pending for this particular work. Finally, instead of looking at the soil, if we can simply bio modify the geotextiles, I'm sure this is going to become more effective reinforcement and thereby improve the efficiency in reducing, as I'm increasing the interface. I'm sure now we can reduce the quantity of geotextiles or geomaterial which are bringing in as an extra addition to this particular soil, and thereby we can reduce, or we can bring in efficiency. We can bring in what you call extra material. We are reducing the extra material into the soil, and finally optimizing the cost and given conditions. Few of the references, which includes also my papers as a part of the work which I presented here. And again, I would like to thank all of the organizers, especially the Institute of Engineers, MegaFerry, and also the international partners who have given me or selected me for this particular presentation and given me the opportunity to present the work which I'm doing. Thank you very much.
Thank you, Professor, for a very energetic presentation. So we'll be taking the question answer session after one of the more session, and then we'll
Sure.
have that
Okay.
session. So
Mm.
before that, we have already mentioned that at 2:40 we will start with the smart quiz. So exactly at 2:40, I will be reflecting my screen with a QR code. You can scan that QR code and start the quiz. Quiz will be for 20 minutes, and in this 20 minutes, you have to answer 35 MCQs. And the questions in the quiz are mostly from the presentation that we have already seen in these 2 days. And please feel free to answer all the questions. And in the starting of that questions, you will have to fill few details like your name, your email ID, and your contact, so that these details are required, so that if someone is the top scorer will be contacted with the help of those details. So I'll be sharing my screen in another 1 minute, and then we can start. And the criteria is like there is that the top scorer, each question contains 1 mark each, and the top scorer will the top fastest scorer will be awarded. So I'm just reflecting my screen. So I think everybody can now see my screen, which has the QR code, right? Tanmay sir, can you confirm, please?
It's visible.
Yeah. Thank you.
Sumit, if they have any query, should I allow them to unmute? Sumit, are you there?
Yes, sir. Please, you can allow them for this session only, na? For quiz you are talking about, I think.
Right, right,
Right?
right, right.
Yeah, yeah, please, please, please. Dear all, if you are facing any sort of issue while filling this quiz, so just you can unmute yourself and maybe you can confirm us, or maybe you can type in the chat box or Q&A session. Q&A
Mhm.
Q&A link that you can see at the bottom center of your screen.
So I see a raised hand from N. Minakshi. Minakshi,
Okay.
may I request you to unmute and in case you want to ask something?
Probably they cannot see the unmute option on their device. You can, anyways, you can type in the Q&A section.
Right.
Please use this link. Welcome, Dr. Reddy. So, yeah, so basically, we are having this quiz right now,
Okay.
and in another 10 minutes, we'll start with your session. So, at
Okay.
2:40 to 3, we have kept this quiz for all the attendees.
Okay.
So, so, also one announcement, if you are facing any sort of issue while filling this quiz or maybe accessing the link we have shared in the Q&A section, please write on the Q&A section and we'll respond to you, okay? Yeah. Yes, sir. Please tell me. Sir, Dr. Dr. Satyanarayana Reddy, sir.
Yeah.
So I think just give one more minute to the audience because 20 minutes it's like at 3:01. So just after that we'll start. Okay, sir.
Okay, sir.
Yes, sir. Please share your screen. Thank you all. From now this point onwards, we'll be not taking the all the inputs that we have received will be considered for evaluation, which is till 15:01. That is 3:02, 3 o'clock and 1 minute. After before only on all the submissions before this will be considered for evaluation. Thank you. Thank you so much. Now continuing, now coming back to the track and continuing our final session for today's session. For today's second day of the Reinforce 2025. Up next is Dr. CNV Satyanarayan Reddy, who will present on reinforced earth retaining walls and industrial byproduct as fill material. Dr. CNV Satyanarayan Reddy, professor at Andhra University, has more than 3 decades of experience in geotechnical engineering. He has received several prestigious awards, including Engineer of the Year and AP State Best University Engineering Teacher. He has guided 17 PhD scholars, published 128 papers, and holds 14 patents. He is fellow of IEI and IGS and lifetime member of IRC and ICI. Please welcome Dr. CNV Satyanarayan Reddy.
Thank you, Sumit, for your nice introduction. So I am happy to be here to share some of the work that is done at Andhra University on using some industrial byproducts as fill material in reinforced earth retaining walls. So hope slide is changing.
Yes, sir.
Yes, sir, it is changing. We are at second slide called Introduction, the concept of reinforced earth.
Yeah, fine. So, as you know, the reinforced earth is a revolutionary innovation in the field of geotechnical engineering, and it is being extensively used in construction of various civil engineering structures during the last 2.5 decades. The major application of reinforced earth is in construction of reinforced earth retaining walls. As you know, once upon a time, construction of retaining walls in the bridge approaches of flyovers, even for retaining soil in hill slopes was the job of a structural engineer, where we used to go for gravity retaining walls, cantilever, and counterfort retaining walls. Nowadays, construction of retaining wall is completely geotechnical engineer's job. So we are seeing quite often reinforced retaining walls, right? In wherever you go to a bridge approach or flyover approach, right? You see reinforced retaining wall. So the main reason for reinforced retaining walls taking over conventional concrete retaining walls is due to their economy and also sustainability. As you know, construction of reinforced retaining wall doesn't require skilled labor, and moreover, these walls are flexible in nature, and they will be able to resist earthquake loading in a better manner compared to conventional concrete retaining walls. So if you look at the section of reinforced retaining wall, you can see from here, for retaining backfill of given height, we will be constructing reinforced retaining wall using a selected soil as fill. Generally, the selected soil will be a frictional soil, or if it is not available, it will be coastal-frictional soil. Such material will be reinforced with either strip, sheet, or grid type of reinforcement. So initially, construction of reinforced retaining wall started with metallic strip type of reinforcement, and later with the advent of geosynthetics, now the present reinforcing material which you find is mostly a geogrid, even parawebs you might have seen, and even woven geotextiles, stiffer woven geotextiles can be also used as reinforcing material. And apart from fill and reinforcing material, the other component of reinforced retaining wall is fascia wall. It is meant for providing local stability for the fill in between the reinforcing layers, and it provides aesthetic appearance to the structure. So there is no special foundation laid for reinforced retaining wall except for having a leveling pad over which fascia wall is erected. So fascia wall is formed using precast concrete panels, or even we can have a gabion wall to serve as a fascia wall. So you can see from here, the major component of reinforced retaining wall is fill. So that's why it is very important to us. The stability as well as cost of reinforced retaining wall depends mainly on fill material. So later, in design, while proportioning, I will ask you to recollect. Generally, the base width initial proportioning will be taken as 0.7 times H, where H is height of backfill plus depth of foundation, taken as 0.1 times height of backfill to be retained. So the minimum base width to be provided shall not be less than 3 meters. So the conventional fill materials that were initially used in construction of reinforced retaining walls are sand, morum, that is silty gravel, and subsequently, due to scarcity of sand, even rock floor was tried as fill material. So as predominant material is fill material, instead of depending on conventional materials, which are becoming costly due to their more demand in other construction activities, it is better if we can explore some industrial byproduct which meets the requirements for use as fill material. It will not only help in safe disposal of the industrial byproduct, but also it will help in reducing the cost of reinforced retaining walls. So as you know, compared to conventional retaining walls, reinforced retaining walls with sand, morum, they are economical by 30 to 40%. If you are able to replace the conventional fill materials by some industrial byproducts, the cost is going to reduce still. So in the present presentation, I am going to cover two industrial byproducts, namely copper slag and silicomanganese slag. So copper slag is a byproduct obtained from matte smelting and refining of copper. So about 2.2 to 3 tons of copper slag is generated as waste for every 1 ton of copper produced. And as on today, worldwide, if you see, there is copper slag production of about 40 millions. And our country, India, the slag generation is up to 1.63 million tons. The copper slag used in the present study is procured from Sterlite copper, Thoothukudi, Tamil Nadu. So if you look at the constants present in copper slag, it is containing ferric oxide of 58.4% and gas silica of 29.2 with traces of CaO, MgO and zinc and copper. So US Environmental Protection Agency regulations have listed copper slag as non-hazardous material, and some of researchers have tried to use copper slag as substitute to fine aggregate in concrete making because of presence of silica and ferric oxide. So it is a granular material. Coming to having most of its particles of the size of right sand. So coming to other industrial byproduct, that is silicomanganese slag. So as you know, silicomanganese is a ferroalloy used in improving mechanical properties of steel. This slag is generated during carbothermic reduction of raw materials inside submerged arc furnace. So huge amounts of slag is generated every year and it is directly dumped in landfills without any significant reuse. So our India is second largest producer of this slag, about 3 million tons annually. This silicomanganese slag is being generated. So this material, pulverized silicomanganese slag is a granular material and hence its suitability for use as fill material in RE walls and in concrete making has been investigated by few researchers. Before using this slag, we need to remove the floating particles, right? So if you pour this slag into water, you will see, right, some amount of particles, right, floating to the surface. So such material need to be eliminated before using it. So the slag consists of, so you can see from the picture, it consists of irregular shaped particles with rough surface and voids as one combination, and other as solid crystals of dull white, bluish green and brownish green color. The material is lightweight and predominantly contains sand-sized particles. So this silicomanganese slag has been procured from Abhijit Ferrotech Limited, located in Achyutapuram in Visakhapatnam, Andhra Pradesh. So looking at chemical composition of silicomanganese slag, so it is containing Al2O3 of 18-24%, silica 36 to 38%, and calcium oxide is also there, 14 to 16%, and manganese oxide, right, 13 to 15%. So some of the leaching studies, long-term leaching, they have reported leaching of, right, manganese in small proportions, but such leaching is not a matter of serious thing. It is not toxic. Only thing is hardness of water will increase a little if water table is present at shallow depth. Except for that, there is not much toxicity associated with this material. So in the present study, besides assessing copper slag and silicomanganese slag as fill material, in designing reinforced retaining walls of varying heights from 4 to 8 meter, Moram conventional fill material, Moram has been also considered as fill material, just to compare how the design requirements are changing with respect to these industrial byproducts in comparison to Moram. So the Moram used in the present study contained 48% of gravel, 38% sand, rest fines, and it is non-plastic material having a liquid limit of 20%, and it is classified as silty gravel. It has maximum density of 2.05 and its shear parameters in OMC MDD and saturated condition, that too in drained direct shear test they are reported. So it has effective angle of internal friction of 33 degrees, and when its interfacial shear parameters are assessed from pull-out test, it yielded values of interfacial shear parameters above the interfacial shear parameter obtained in a drained condition on the material itself. In such a case, we need to limit it to the same value 33. So here it is 33, right? By mistake, it is typed as 35. It is limited to 33. Similarly, with respect to silicomanganese slag, you can see specific gravity is low, 2.05, and it contained 100% sand size particles only. It has uniformity coefficient of 3.2 and CC of 1.1. It is a non-plastic material. Equivalent IS classification symbol is SP, and it has maximum radial density of 1.13 at OMC of around 6%. It has exhibited a much higher frictional characteristics compared to Morum, and its interfacial friction angle with woven geotextile used in the study having 60 kN per meter strength, kilonewton per meter tensile strength, thickness of 0.61 mm and 240 GSM. It yielded value above 41, so it is limited to 41. So coming to copper slag, it is heavyweight material. Specific gravity, you can see it is higher than even Morum, and it is 3.34. So it also contained predominantly sand-sized particles, and it has a uniformity coefficient of 3.2 and the CC close to 1.8, and the equivalent IS classification symbol is poorly rated sand, SP. Compacted maximum radial density was 2.35, and its angle of interfacial friction is 38 degrees. So looking at the requirements specified by Jones for fill materials, with respect to frictional fill, our materials are frictional fills. So percentage fines shall be less than 15. We have only 0% fines for silicomanganese slag and copper slag. Angle of interfriction shall be greater than 25 degrees. Coming to CU, it is only just above 3, not above 5. CC, of course, for silicomanganese slag greater than 1 and copper slag 0.8 close to 1. So if you go by Jones criteria, you will feel the CU is 3, it cannot be used like that. So anyway, I will also show you IRC special publication requirements, and then we will assess. So if at all frictional fill is not available, then you can use material with fines more than 15%. For such a thing, Jones has given specifications. So anyway, for our case, frictional fill specifications are required. If at all we are using metallic reinforcement, then we should also look at chloride and sulfate content. But since we are dealing with synthetic reinforcement these days, so these specifications are not required. So coming to requirements laid down in IRC SP 102, you can see if a soil or material is having percentage fines less than 15 and satisfies this gradation criteria, plastic index less than 6, in our case it is non-plastic, and if CU is greater than 2, it recommends for use as a frictional fill. So in case of soil, or if you have any industrial byproduct granular in nature with percentage fine greater than 5, then greater than 15, then you should look at percentage of particles passing 15 micron sieve. If it is less than 10, then you should look at the plasticity index. If it is less than 6, and if you see angle of internal friction above 30 degrees, IRC recommends to use it as fill material. So as per IRC specification for CU, our materials are passing as the CU values are greater than 3. So in the present study, design of reinforced retaining walls has been done, considering both external and internal stability mechanisms. So you might have seen, right? Reinforced retaining wall external stability analysis need to be done by considering reinforced retaining wall as a rigid body, and under the action of lateral thrust coming from backfill and other live loads and dead loads acting on the proposed RE wall, you need to assess its stability against sliding failure, overturning failure, bearing failure, and slip failure. Since the width of base width of reinforced retaining walls is large, generally sliding failure does not, generally overturning failure does not happen. So generally we need to check for sliding, bearing failure. So whatever base pressures that are transmitted from RE wall due to lateral thrust from backfill and other loads that are acting, maximum base pressure induced at toe shall not exceed safe bearing capacity of soil. If it exceeds, we will have risk against occurrence of shear failure. If at all we construct RE wall on soils of low shear strength, then we may have the chances for occurrence of deep-seated slip failures. So in the present study, since we have considered silty sand prevailing in our Andhra University campus, same thing we have used as backfill material as well as foundation soil. So this slip failure analysis is not done. So after getting satisfactory required factors of safeties in external stability mechanism, then the reinforcement, tensile strength and length of reinforcement, particularly beyond the rupture plane within the reinforced earth fill, have been arrived by giving due consideration to pull-out failure of reinforcement and tension failure of reinforcement. So here you can see external stability involves consideration of reinforced structure, that is RE wall as a whole, as a rigid body, and checking its stability against sliding, overturning, bearing failure, and slip under the effects of backfill thrust, dead loads, other loads. Coming to internal stability, it involves considering internal mechanisms, namely tension and pull-out failures due to shear within the reinforced earth wall. So accordingly, right, it deals with the arrangement and the requirement of tensile strength, right? A length of reinforcement required to be provided for internal stability. Those aspects we will be dealing. So you can see when sliding occurs, when lateral thrust from backfill exceeds the frictional resistance mobilized at the base of the wall, sliding failure will occur. Overturning failure takes place when the overturning moment caused by the lateral thrust coming from backfill exceeds the resisting moment available due to self-weight of the wall, it will overturn, right? So generally we maintain a factor of safety, minimum factor of safety of 2 against overturning failure, and against sliding failure you will see factor of safety of 1.5. So coming to bearing capacity failure risk, we determine the base pressure distribution, either trapezoidal base pressure distribution you can take due to the resultant vertical loads and the moment caused by lateral thrust, due to direct compression and bending, right, due to moment, you will have higher pressure, base pressure near toe and lesser pressure at heel. So if it is overstressed, if Qmax is exceeding safe bearing capacity, so there will be differential settlement and it may tilt. So whenever you are constructing RE wall on soils of low shear strength, you may anticipate deep-seated slip failures. This requires doing stability analysis with number of trial slip circles and establishing critical slip circle as the one having least factor of safety. On such critical slip surface, we should have a minimum factor of safety of 1.5 for long-term durability. Coming to internal stability mechanisms, so within the reinforced earth wall, we consider rupture plane. So practically rupture plane will be covered, but in analysis, when we do it by tieback wedge analysis, wherein we use Rankin's theory, So the rupture plane is taken to be planar, replacing the actual chord one. That rupture plane separates the reinforced soil mass into sliding zone and stable zone. So if at all the tension induced in reinforcement layers due to the lateral pressure transferred by the fill on back of fascia, the tension pulls the reinforcement. If length of reinforcement available beyond rupture plane is small, then what happens is when the induced tension exceeds the frictional resistance available on both sides of the reinforcements, it will get pulled out, right? So when pull out of reinforcing layers happens, the sliding wedge along with the pulled out reinforcement will move. If at all the provided base width of your retaining wall is more, that means length of reinforcement is more, and if length of reinforcement beyond rupture plane is large, then you will have high frictional resistance or pull-out resistance available. If you use reinforcement material with low tensile strength, the possibility is it will break, right? So that is called tension failure. So in design, we take care of both the pull-out failure by maintaining adequate bond length or anchorage length for reinforcing layers beyond rupture plane, and also we adopt the ultimate tensile strength of reinforcing material in such a way that tension failure does not happen. So design of reinforced retaining walls has been done for backfills of height varying from 4 to 8 meters as per British standard 8006 part 1 2010, using Morum as fill material, and also designs are carried out using the byproducts under study copper slag and silicomanganese slag for both non-seismic and seismic conditions. So the backfill material considered in the study was the local available soil at Andhra University, that is silty sand, which has a dry density of 1.82 gram per cc. Saturated density, if you find, it will be around 2.1 gram per cc, taking specific gravity as 2.66. It has angle of internal friction of 31 degrees. So a uniform surcharge of 24 kilonewton per meter square has been considered to be acting on the wall for design. So after preliminary proportioning, that is by fixing depth of the foundation, that is 0.1 times height of the backfill. Adding that to height of backfill, you will get capital H, and then base width is fixed as 0.7 times H, subject to minimum of 3 meters. Right, as per that class, preliminary proportioning is done. So width of retaining wall is nothing but width of reinforcing layers. Generally, we'll take like that. So the external stability analysis is performed as per British standard. So as I mentioned, water-turning failure generally does not occur. So that I am not covering here. Directly bearing and tilt failure. So if your retaining wall is rigid, determination of Qmax and Q minimum trapezoidal pressure distribution is valid. If retaining wall has rigid behavior, our reinforced retaining wall is flexible. Generally, the bearing pressure we will calculate using Meyerhof pressure distribution using effective width base width concept, right? So as per that, bearing pressure is determined as RV by B minus RE, where RV is resultant of all factored vertical load component, right? So here a factor of 1.5 is used to get the ultimate load with respect to working loads. Eccentricity is determined as the ratio of water turning moment to the factored vertical loads, even moment and if you are taking one thing factored, other things should be also taken as factored one. Then we need to compare this with safe bearing capacity. as per the procedure suggested by British standard. So as per that, we should calculate safe bearing pressure on foundation soil as Q ultimate by FMS. Q ultimate you can determine as per our Indian standard 6403. You divide that with partial safety factor applicable to foundation soil 1.35 recommended by British standard, and add gamma dm or burden depending upon depth of foundation provided for your wall. Similarly, the safety against sliding is checked by considering soil to soil contact and by ensuring that Fs times RH is less than or equal to RV times, that is resultant vertical load times tan phi dash by FMS. So tan phi dash is nothing but mu, right? Coefficient of friction. So we need to apply partial safety factor of 1. This is suggested by British standard only 1. So second term does not arise because our materials are frictional materials. There is no cohesion. So the second term is immaterial. So partial factor against sliding specified in British standard is 1.2. So if you calculate RV times tan phi dash by FMS, and if you calculate 1.2 times the disturbing force, right? That is horizontal lateral thrust coming from backfill, right? If you satisfy this criteria, Fs into RH less than RV times this, you can say your proportion RW is safe. Next, coming to internal stability analysis, as you know, there are two methods, namely tieback wedge analysis and core and gravity analysis. In our study, we have used tieback wedge analysis. So tieback wedge analysis assumes, right, Rankine's equilibrium condition, and thereby we take, right, the inclination of potential, right, failure plane or rupture plane to be inclined at 45 degrees phi f by 2, where phi f is angle of neutral friction of fill. So this rupture plane separates reinforced fill into active and resisting zones. And in Rankine's theory, coefficient of active earth pressure is taken to be constant at all depths, 1 minus sin phi f by 1 plus sin phi f. Here we assume the fascia wall to yield about the base so as to mobilize the active conditions on back of it. So in internal stability analysis, I need to determine tension induced in each of the reinforcing layers. Suppose if you take a reinforcing layer here, the tension induced in this layer is due to lateral pressure acting on the back of, right, fascia wall. So for that, if you know vertical stress here, you multiply. So if you know vertical stress, you calculate what is the horizontal stress by multiplying it with the, right, K. In this case, active condition, so Ka gamma H. So you multiply that with the area, extending half the vertical spacing above and half the vertical spacing below. So in tieback wedge analysis, to ensure safety against tension failure, so after determining tensile tension induced in each layer, we should see that the ratio of design strength by partial safety factor accounting for economic ramifications of failure shall be greater than Tj. It should be satisfied for all the layers. And to avoid pullout of any of the layers, we should have adequate right, surface area at top and bottom of the reinforcing layer. In case of sheet and grid layer, we calculate per meter run. Right, so surface area you can say as the total horizontal width on top and bottom faces multiplied by 1. So such a thing, the required top and bottom surface area, mobilizing frictional ratio shall be greater than Tj by the term in denominator. Here also second term does not arise. So in fact, the term that is there in denominator is the pullout resistance contributed by friction and contributed by cohesion. So when you have interaction between reinforcement and cohesion, we should not say cohesion adhesion, right? So since our material is frictional fill, the second term is not there. So various parameters associated with calculation of pullout resistance due to overburden pressure and surcharge, right, due to dead loads is given below, and various partial safety factors that are to be applied are mentioned here. So here LEJ is the length of reinforcement beyond the rupture plane where the pullout resistance acts. It's not the full length of reinforcement in RE wall. You have to take length of reinforcement extending beyond rupture plane. So after ensuring the safety of reinforcement against pullout individual layers. So generally for pullout, topmost layer is right more susceptible. For tension failure, since vertical stress acting on bottom layer is more, so obviously the lateral pressure acting on right fascia wall inducing tension will be large. So that's why bottommost layer is more prone to tension failure. So in addition, we need to do the wedge stability check. So in this, we consider various potential failure wedges and whatever reinforcements that are falling within those wedges. So we calculate the tensions induced in those layers, sum them up, and whatever frictional resistances you work out for those reinforcing layers and sum them up. So that combined pullout resistance or frictional resistance shall be greater than sum of tensions induced. Similarly, if you take design tensile strength and divide with partial factor accounting for ramifications, right? The sum should be greater than the sum of tensions induced in the reinforcing layers. So these two conditions, if you are satisfying it, means that there is no chance of any wedge failure due to tension failure in reinforcements or pull out of the reinforcing layers. So coming to calculation of induced tensile forces. So tension is induced, right, due to sulfate of fill and surcharge. If any dead load is acting on surface, due to that also you need to calculate. So anyway, in our design, we have calculated only tensile force due to sulfate of fill and surcharge. So in a reinforcing layer, at a certain depth, let us say that layer as jth layer. So the tension induced in that layer you can determine as the vertical stress that is acting at the level of reinforcing layer multiplied by coefficient of active earth pressure. So here also it should be specifically KAF, coefficient of active earth pressure of fill material, and you need to multiply this lateral pressure with the area extending half vertical spacing above and half vertical spacing below, because and per 1 meter length we calculate. So we need to multiply this lateral stress acting on back of fascia with the area of influence of the layer under consideration. Okay, so here the vertical stress is calculated resulting from sulfate of fill and the uniform surcharge that has been considered. So again, sigma Vj you can calculate at the level of reinforcement using Meyerhoff's pressure distribution using the relation Rvj by Lj minus 2Ej. Here Lj is length of reinforcement right under consideration. So generally length of reinforcement will be equal to width of reinforcement at the retaining wall. Eccentricity you need to calculate by dividing overturning moment with the resultant vertical load acting at that reinforcing layer. So coming to seismic design in external stability analysis. So in addition to lateral thrust coming from backfill under static condition, you need to add inertia force, which is 0.5 gamma h square by alpha hm, where alpha hm is mean horizontal seismic coefficient, and you need to add 50% of dynamic thrust, right? So for calculation of inertia force, expression is written here. Alpha hm we will calculate as 1.45 minus alpha h into alpha h. Alpha h is horizontal seismic coefficient. It is determined using seismic coefficient right method for zone 2, right? Beta into I alpha, right? And that formula, you know, alpha h. From that, by substituting the value of beta I and alpha, you'll get alpha h. And using Monod-Bay, Okabe expression for coefficient of active earth pressure in seismic condition, you can calculate what is the dynamic thrust, right? 50% of this will be added to inertia force in addition to the static force which you have due to backfill pressure. So coming to internal stability, the induced tensions in reinforcement layers will be also increased due to inertia forces. So in addition to maximum tensile force which you are getting from right static analysis, non-seismic condition, you need to add delta TMD, where delta TMD is determined as the total inertia force divided by sum of reinforcement lengths beyond rupture plane from all layers multiplied by layer under consideration. Okay, so the total inertia force is calculated by multiplying the weight of sliding wedge, that is weight of soil wedge in active zone, with the mean horizontal seismic coefficient. So while determining right the pull-out resistance from the fill onto reinforcing strips in anchored zone, that is beyond rupture plane, generally the resistance will be reduced by 20% because there will be vertical accelerations and thereby there will be some reduction vertical stress. So R seismic will be taken as 0.8 times R static. So here I am showing, I am presenting the details of design that is carried out for backfills of varying height using 3 different fill materials. One is conventional Morum, the 2 are industrial byproducts. So you can see from these slides, so you see factor of safety against overturning is always very high, right? So even if you do not check also, doesn't matter, but there is a case where you need to check where it may fail, that I will tell. So if you look at induced bearing pressure, so for a given height, let me say 4 meter, 245 kilonewton per meter square is the induced base pressure. Copper slag is inducing 262, whereas silico-manganese slag is inducing 204. So silico-manganese slag usage for retaining backfill of given height, you can say it will induce lesser bearing pressures. So even if you have soil with relatively lesser bearing capacity, you will be able to construct a RE wall. So compared to conventional retaining walls, the requirement of bearing capacity for reinforced earth retaining walls is less. Even in reinforced earth retaining walls also, if you are going with lightweight fill material, then requirement is going to reduce further. That is the advantage of silico-manganese slag. So copper slag, since it is heavy material, it has resulted in increase in right bearing pressures. So unless you have reasonably good foundation soil, don't select copper slag though it is available local. So coming to induced tensions in the reinforcing layers, maximum induced tensile force in reinforcements. You can see for a given height, silicomanganese slag has resulted in least tensile force, and even copper slag, though it is a heavier material, it has resulted in lesser tensile force. This is due to its better frictional characteristics. Right, so the tension induced in reinforcing layer not only depends on the unit weight of the material, but also on its frictional. Higher the angle of interfacial friction, the lesser will be the tension induced in the reinforcing layer. Higher will be the pullout resisting force generated. So coming to the seismic design pertaining to zone 2. So very marginal differences have been noticed. Not much change in the design parameters were observed. So whatever initial proportioning that is done for a non-seismic case was observed to hold good for seismic case also. However, a slight increase in induced tensions were there. Even here also, silicomanganese slag yielded relatively lesser induced tensions. Even bearing pressures also same trend. So look at factor of safety against overturning. So here for silicomanganese slag at smaller heights, the factor of safety against overturning has gone below 2. So that's why whenever we are using lightweight material, when you are doing design for seismically active zones, it is better you also check for overturning. There is a possibility for having risk against overturning failure. Okay, based on the design of reinforced retaining walls performed for non-seismic and seismic conditions using conventional fill material Morum and industrial byproducts silicomanganese slag and copper slag. We can draw the conclusions that are listed here. The gradation characteristics of copper slag and silicomanganese slag satisfy the requirements of frictional fill material. Particularly, they are satisfying the criteria specified in IRC special publication. So both the slag materials have higher pullout resistance in comparison to Morum due to more roughness of the particle surfaces. And the copper slag induced bearing pressures of about 5 to 9% more compared to Morum due to its relatively higher density, whereas silicomanganese slag induced lower bearing capacity by about 14 to 20% as it is lightweight material. Due to greater angles of shearing resistance, the slags offered better resistance to seismic loading and induced lower tensile forces when compared to Morum. Non-seismic designs of reinforced soil retaining walls under study are adequate to withstand the seismic loading of zone 2. So we can't say in highly seismic zones, zone 4 and 5, a slight revision in design parameters, will be required. But in zone 2 and to some extent zone 3, you will not find no significant change in design requirements. The induced tensile forces in reinforced retaining walls with copper slag are observed to reduce by about 10 to 13% compared to reinforced walls with conventional fill material Morum in both seismic and non-seismic. Similarly, coming to silicomanganese slag, the reduction in induced tensile forces was up to 50%. So what we can say is you can consider using copper slag as an effective alternative to conventional fill material, where you have soils with good bearing capacity. And you can consider using silico-manganese slag, particularly for building reinforced retaining walls of larger heights. And also at locations where soils have relatively lesser bearing capacity. So with this, I close my presentation. So if there are any questions, I'll be happy to answer.
Thank you so much, sir. It was a very detailed presentation, and I'm sure attendees would have liked this. So I think with this, we can start with the Q&A session. And I shall request Dr. Satyanarayan Reddy and Dr. Uday sir to be available. And in the meanwhile, I'll just start with the questions. Okay. Okay, so first question that we have with us, Professor, how does the change in climatic condition can affect the biocementation measures like MICP of the erosion protection measures of slope? Question is from Mr. Mandal. And
Just give me a minute. Sorry.
yeah.
Yeah. Am I audible?
Yes, you are.
Thank you. Okay. So the question definitely is interesting because the major aspect of the climate related aspects majorly affect definitely the biocementation, at least in the initial process. So should I simplify the point saying that yes, we can do the initial process of MICP during the hot and dry season. Later, when the wetting season starts, by the time if the setting is happening, then surely there will be no further effect of the climatic conditions on biocementation measures. However, if we try to do the process during the wetting or during just after the wetting period or when the soil is totally moist, then because understand that this is bacteria we are talking about, it also needs the urease as well as the air to develop the environment for secreting the cementation. So it might not be very effective during the wetter periods. However, in the drier periods, as I told you, it will be definitely much sequential or much advantageous.
Thank you, sir. Thank you for taking this question. Another question on the same topic. What is the average life cycle of biocementing bricks as it is biodegradable?
Okay. While definitely biocementation bricks is slightly out of the domain, I worked on it earlier. We did some testing. The quick answer again for this will be, if I understand the question, I understand that you are talking about the average life or life cycle, because life cycle is a different word when we talk about the what is the sustainability index we use. Life cycle normally a word, but if I answered the question on the time of taking it as an average life of the biocemented bricks, then because we are because the bacteria or the enzymes are giving you the best form of calcites, which are bonding or bridging the soil particles, it is as good as you are adding 100% lime into the into the bricks. So the degradation process and everything is now as per the environmental conditions, and it can be promised as good as a regular cemented bricks. However, the conditions again like pH or the presence of sulfur or chlorine in the environment will definitely affect the regular condition of the cementing in the bricks. If we talk about the life cycle of the biocementation bricks, then definitely we are talking about a very sustainable process on which we are getting the calcites compared to mining or any other condition. Then I'm sure the life cycle of biocemented bricks is much more sustainable than a regular cemented bricks. If I could answer both the parts of the question. Thank you. And by the way, initial part of the cementation is biodegradable. Once the cement sets, like the regular curing period we have, then it is no more biodegradable. Thank you.
Thank you, sir. I think we have another question from Dr. Biju, and this question is to Dr. Uday only. Have these solutions been adopted practically for any RT walls, retaining walls?
Okay, sir. The current work, whatever I have presented, either the bioengineering or the biobacterial concrete or bacterial cementation, neither of the works have been taken to field, while the students already started the scale tests on different conditions. So currently, I may not be ready to give you the answer. We did not try yet in any of the field application directly. I'm sure this will take a good amount of time to get into the field, and because we also need to give confidence guarantee as well as the monitoring aspects which need to be considered again in this case.
Thank you, sir. I think we can move to quickly next set of questions. So next question that we have is from Mr. Sikar, and question is, shall the geosynthetic reinforcement be embedded over the fascia wall, allow at each layer level, or only over the fill material? This question is for Dr. Satyanarayan Reddy.
Yeah. So generally, geosynthetic materials are embedded in fill, connected on the back of the fascia panels. So except in case of reinforced earth retaining walls constructed using geotextiles with wrap around, wrap back technology, their geotextile will be exposed to sunlight. In such a case, you have to use black carbon coated geotextiles to protect from ultraviolet rays.
Okay. Thank you, sir. Just a point that I want to mention that which is bit disaligned from the questions that we are taking. So just after this Q&A session, we'll be having the concluding session, after which Dr. Ratnakar will be announcing the quiz winners. So and we are glad that we have received more than 100 responses, attended responses. And out of these, we have 3 winners among all these more than 100 participants. So now aligning our track to the Q&A session again. Next question is again from Dr. Reddy, and question is, Professor, does there any study on the determination of reduction factor related to the interaction of polymeric reinforcement and selected backfill, namely copper slag or SIMN slag,
Silicon
I
manganese
think
slag.
silicon magnesium slag, namely installation damage factor, chemical degradation factor. So this is the question, sir.
Right now, specific to those materials, separate factors are not available. Whatever factors that are recommended for general fill materials by BS code, those things only we are using. So specific to these slag materials, if someone can work, it can be a good topic for research as well.
Okay. Okay. So thank you, sir. Next question that we have is, Professor, there is to again Dr. Reddy. Does there will be any kind of leaching effect for the soaking of industrial byproduct in case of using the same in selected backfill for RERS walls? Thank you. This is the question.
Yeah, with respect to copper slag, there is no problem with leaching and all, right? No toxic elements are present and leachable. Coming to silicomanganese slag, also I told you, only manganese long-term leaching effect has shown, right? Traces of manganese leached into underground. So if water table is deep and if you are not allowing water to stay and percolate for a longer period, you need not bother much about it. If at all any such case also, before constructing RE wall, while preparing foundation bed, you embed some membrane so that leachate does not go and pollute underground. Only thing if you don't take proper care while using silicomanganese slag is, if water table is at shallow depth, its hardness may increase. Other than that, there is no toxic effect.
Okay. Thank you, sir. Thank you very much. With this, we will conclude the final Q&A session. And I would like to thank Dr. Reddy. In fact, with this, we are at the end of the session, near to the concluding session of this 2 days virtual global platform, where we were able to share the thoughts from the eminent speakers from the geotechnical industry. And at the end, I would like to thank all the speakers from day one and day two. From day one, Dr. GL Siva Kumar Babu, Dr. Ashish Juneja, Dr. Satyajit Patel, Mr. Gianluca Spadaro, Dr. Ratnakar R. Mahajan, Mr. Pierluigi Basito, and Dr. Amit Prashant. And from day two, Dr. Madhvi Lata, Dr. A. Murali Krishna, Mr. Rudra Budbati, Dr. Venkat Udekala, and Dr. CNV Satyanarayan Reddy. So with this, we can start with concluding ceremony. And I would like to, for this, I would like to call upon Mr. Ashok Kumar Basa, who is a distinguished structural engineer with nearly 4 decades of experience in bridge design, hydraulic structures, rehabilitation of projects, a past president of Indian Institute of Engineers. He is currently serving as the Executive Vice President of the World Federation of Engineering Organization, also known as WFEO. He has held key roles in BIS and IRC technical committees and contributed extensively to the National Engineering Standard. Internationally, he has represented India at numerous WFEO and UN forums and chaired several WFEO committees. I would like to call upon Mr. Basa.
Good afternoon. Am I audible, first of all?
Yes, you are, sir.
Excellencies, revered dignitaries, esteemed colleagues, and distinguished delegates. It is both an honor and privilege to join you at the valedictory session of Renforce 2025, an exceptional confluence of global minds, technical brilliance, and shared commitment towards a sustainable future. Over the past 2 days, we have witnessed an extraordinary exchange of ideas and innovations that reaffirm our belief in the power of engineering to shape a resilient and a circular world. Organized by the Institute of Engineers India in association with McAfee and supported by the World Federation of Engineering Organizations, this conference has brought together pioneering solutions from climate-resilient infrastructure to bioengineering, geosynthetics, and smart monitoring systems. These are not merely technologies. They are instruments of transformation that respond to the pressing global challenges of climate change, urban stress, and environmental degradation. As Executive Vice President of World Federation of Engineering Organizations, I take great pride in witnessing the alignment of this conference with WFE's mission, that is, to advance the role of engineering in achieving the United Nations Sustainable Development Goals. Forums like Renforce 2025 embody our collective aspiration to harness engineering for societal good, ensuring safety, inclusivity, and resilience in every project, policy, and profession. I'm heartened to see the growing involvement of young professionals and researchers and engineers who are not only solving today's problems, but are also reimagining tomorrow. Their work represents a new paradigm where innovation meets responsibility. On behalf of World Federation of Engineering Organizations, I commend Institute of Engineers India for its visionary leadership and McAfee for its technical stewardship in bringing this global platform to life. I assure you that World Federation organizations will continue to support such initiatives that bridge regional expertise with global advocacy. Let us carry forward the momentum of Renforce 2025 to our workplaces, institutions, and policymaking forums with renewed resolve and resound. Together, let us reinforce our commitment to ethical, resilient, and sustainable engineering. At the end, I conclude with a prayer to Almighty on behalf of all of us. Oh God, please give us the courage to change things we can. Oh God, please give us the courage to change things we can, the serenity to accept things we cannot change, and the wisdom to know the difference between them. Thank you and join in. All the best to you, all of you. Thank you.
Thank you, Mr. Basa, for your kind words. So now moving next, we are honored once again to welcome Mr. Naveen Chandra Vasoya, a renowned chemical engineer and dynamic industrialist. Mr. Vasoya is the past president of Institute of Engineers India and currently serves as the National Member, Executive Council, WFEO, and Chairman, IMC WFU. With over 2 decades of service to IEI and global leadership roles in WFO, FIAP, and CEC, he has been instrumental in advancing engineering excellence and international collaboration. I would like to call upon Mr. Vasoya.
Good afternoon to all. Am I audible? Ashok
Yes,
bhai?
sir. Perfectly fine.
Ashok bhai? I think I am not audible.
No, sir. You are audible, sir.
Absolutely audible. Looking damn smart also.
Yeah, sir.
The distinguished speakers, esteemed delegates, and colleagues. As we draw the curtains on 2 impactful days of Rainforest 2025, I wish to express my sincere appreciation to all participants who made this conference a grand success. From climate resilient design to bioengineered slope stabilizations and IoT-based smart monitoring, we explored an impressive spectrum of forward-looking technologies. These discussions are not only intellectually stimulating but essential for shaping future policies and engineering standards globally. Is it going okay or anything problem? It's okay, right?
Everything is
Yes,
fine.
you are audible, sir.
Okay.
Yeah.
I am particularly encouraged by the presence of young engineers, researchers, and industry leaders who are driving this momentum. Their energy and innovation will lead us into a new era of sustainable infrastructure. On behalf of WFEO, I commend the Institution of Engineers India and Meka Ferry for creating this vibrant platform. Let us now take this knowledge forward to our institutions, communities, and countries and act upon the ideas exchanged here. On behalf of WFU, again, I would like to express my sincere thanks to our past president, Mr. Ashok Kumar Basa, and Executive Vice President of WFU for his esteemed presence today in this valedictory session. In particularly, I would like to express my sincere thanks to Mr. S.S. Rathore, who is the past president of the Institution of Engineers India and also a past chair of WFEO CIC, that is one of the standing technical committee of WFEO. He was the chairman of this committee for 2 sessions, that is for 8 years. And that was declared one of the best committee in WFEO, performed the activities as per the requirement. Mr. Rathore is at present an advisor to Chief Minister Gujarat. He is also a managing director of Gujarat Metro Rail Corporation. He is also a chairman of Gujarat Maritime Board. So we have received the help to organize this seminar from Gujarat Metro and also from Gujarat Maritime Board, and that is because of Mr. S.S. Rathod. So that is my personal, on behalf of IMC WFPO, personal thanks to Mr. Rathod. Mr. Rathod and his contribution to such type of program, he is a guiding force and inspiration for all of us, and motivate us to conduct such more and more programs. So our sincere thanks on behalf of IMC WFPO, Indian Member Committee, World Federation of Engineering Organization. I really thanks our beloved past president, Mr. Rathod. Finally, I would like to say, let us continue jointly to reinforce resilience, innovation, and ethics in engineering. Thank you all. Once again, my thanks, my congratulations to Headquarter IEI, our President, Mr. V.B. Singh, our Secretary and Director General, Major General Dr. Siali, and Executive of our International Cell, Mr. Tanmay Chakravarti. My sincere thanks to all of you, including Meka Ferry. Thank you very much. Jai Hind.
Thank you, sir. Thank you for your kind words. And now moving on. Now next we are honored to welcome Major General Dr. Mohanjit Singh Siali, VSM, retired, at the valedictory session of Reinforce 2025, a highly decorated Army veteran with over 36 years of distinguished service. He has held key operational, instrumentational, and strategic role across Indian Armed Forces, an academician of rare caliber. He has held multiple advanced degrees, including PhD in physics and gold medalist from JNU, a recipient of Vasisht Seva Medal and COS commendation card. Major General Siali has significantly contributed to defense indigenization and engineering excellence. Since August 21, he has been serving the Secretary and Director General of the Indian Institute of Engineers, India, guiding the institution with visionary leadership and strong commitment to national development. On this, I would like to call upon Major General Siali.
Thank you, Sumit. Respected dignitaries, esteemed speakers, distinguished delegates and partners, as we conclude this two-day journey of learning and innovation in Reinforce 2025, it is my proud privilege to extend a warm and heartfelt vote of thanks on behalf of the Institution of Engineers India. At the outset, I express our deep gratitude to the World Federation of Engineering Organization, WFEO, for their generous support and patronage. We are especially thankful to Mr. Mustafa B. Sehu, President WFEO, who sent a special audiovisual message for this occasion and also joined us virtually for a while during the inaugural session. We are also honored by the presence of Mr. Ashok Kumar Basa, past President, Institution of Engineers India, and Executive Vice President WFEO, who graced the valedictory session with his esteemed presence. His contribution to global engineering cooperation continues to inspire us all. I further acknowledge the leadership of Engineer Naveen Chandra B. Vasoya, the past President of Institution of Engineers, Chairman, Indian Member Committee of WFEO, and National Member Executive Council of WFEO, whose guidance has been instrumental in making this event a global platform for engineering dialogue. A special word of thanks is due to Mr. S.S. Rathod, past President III, Advisor to President WFEO, Co-Chair IMC WFEO, and Advisor to Chief Minister Gujarat, for his continued counsel, encouragement, and efforts that significantly contribute to the successful support and facilitation of this event. I also extend sincere appreciation to our knowledge partner, Meka Ferry Environmental Solution Private Limited, for their integral role in curating technical content and mobilizing global expertise. A very special word of thanks goes to our event sponsors, whose support enabled us to reach and engage a diverse global audience, that is the Gujarat Maritime Board and Gujarat Metro Rail Corporation Limited, And also for this, we wish to thank Engineer SS Rotor once again for ensuring this to happen. And the contribution made by these have been vital for the success of Reinforce 2025. To our esteemed speakers, who are the main part in this, from Indian Institute of Science, Bangalore, Indian Institute of Technologies, National Institute of Technologies, Andhra University, and international institutions like NESA, SRL, Italy, your insights have not only enriched our knowledge, but also ignited meaningful discourse on resilience, sustainability, and circular economy infrastructure. I also thank all the delegates, students, industry professionals, and researchers from across the world for their enthusiastic participation and engagement throughout the sessions. My sincere appreciation goes to the organizing committee, especially Mr. Tanmay Chakrabarti from our II headquarters and the entire team at Macquarie for their outstanding coordination, content planning, and technical support. Further, I thank our moderators, volunteers, and technical staff for ensuring a smooth and seamless virtual experience. As we part today, let us carry forward the spirit of collaboration and the actionable insights that we have gained here, reinforcing our commitment to building a sustainable, future-oriented engineering ecosystem. Thank you once again. Jai Hind.
Thank you, sir. Thank you for your kind words. Next, to conclude this global webinar, I would like to call upon Dr. Ratnakar R. Mahajan, and thereafter he'll be also announcing the quiz winners. I think many people are waiting for that too. So let's welcome Dr. Mahajan, who is working as Regional Technical Manager at Macquarie, responsible for India, Southeast Asia, and Pacific region. With almost 2 decades of experience, he's an IIT Bombay alumnus specializing in soil reinforcement, geotechnical modeling, seismic analysis, ground improvement, rockfall protection. He has been contributing to codal guidelines for the Bureau of Indian Standard (BIS) and Indian Road Congress (IRC).
Yeah, thank you, Sumit. And I think I will not hold excitement too much. So, ladies and gentlemen, as we conclude this insightful online conference jointly organized by IEI and Macquarie, of course, supported by WFEO, I would like to sincerely thank everyone who has contributed to its success. To our distinguished speakers, your expertise and engaging presentations have truly elevated the quality of discussions. We deeply appreciate the time and effort you have put into sharing the knowledge. To vibrant audience, thank you for your active participation and thoughtful questions. I think the sessions were very quite interactive and there was enthusiasm throughout the sessions. So now we are pleased to announce the winners of the online quiz, which is conducted during the conference. So Sumit, I request you to put up the names of the winners. Yeah, so congratulations, Kirutipika P from IIT Tirupati, Harsha Vardhini S from IIT Tirupati, and Guru Swami R from Anna University. So congratulations to all of you. From Macquarie side, we will be giving you the cash vouchers of 2,500 each. Sumit Pathak will coordinate with you and provide these cash prizes. Congratulations once again, and we'll be reaching out to you soon with the details of the prizes, the vouchers. Looking at the overall overwhelming response, and the success of this conference in the series, we are happy to share that we will be back next year, because when we had number of meetings between us and Tanmayji. So Tanmay sir had expressed, looking at the response, IEI feels that this series shall continue. So we will come back to next year. Of course, we'll come back with another theme. We look forward for your continued support and participation. Once again, thank you all for joining us. Stay safe, stay curious, and I say stay connected. Thank you.
Thank you, Dr. Ratnakar. And I think your announcement just came like a sweet, and it was like icing on the cake towards the end of the wonderful session that we had. So, with this, we would like to conclude this session. Thank you all. Thank you all speakers. Thank you all session holders. Thank you IEI team, WFO team, and at the last and most important to all the attendees. Thank you. Have a nice day. Jai Hind.
Thank you.